Okay, let's look at Chapter 4, Section 5 on exponential and logarithmic equations. And this little spiel right here does apply. So you're okay to use calculators in this, but only when you're not asked for an exact solution. And usually I'm going to ask you for an exact solution because that keeps you away from the calculator, kind of helps you get off your calculator dependence, and it focuses you on the mathematical properties of the logarithm. Now that's not true for this particular chapter in the homework. Sometimes they will ask you for an exact solution, and sometimes they will ask you for an approximated solution. When I chose those homework problems, if I recall, it's been a while, I chose most of them where you will be asked for an exact solution. So when we're doing this, I'll try to remind you what the exact solution looks like. The exact solution is always kept in terms of log, and you simplify it as much as you can by using properties of logarithms. So here's some other properties of logarithms. So our values of x and y are both 0, and a, which is going to be the base of our logarithm, by definition is always greater than 0 but not equal to 1. So the following hold. X is equal to y is exactly the same as log a to the base x is equal to log a. Log to the base a of x is equal to log to the base a of y. Another property we'll use sometimes, you can again use notes. For some base a, if I take the base of the logarithm and raise the log to the base a of x, I get x. That has to do with the fact that I'm using the same base here, and the exponent has the log to the base a. We'll talk about it when it comes. And by definition, log to the base a of x equals b, if and only if x is equal to a to b. That's by definition. So by definition, log to the base a of x equals b. That literally implies that if I raise a to the exponent b, then I get x. That's literally by definition. So let's go ahead and let's use some of these properties to solve logs. So remember the domain of the log function, log to the base a of x, is equal to, 0 is not included in the domain, to positive infinity. The range, on the other hand, is equal to minus infinity to infinity. And also recall that log to the base a of 1 is equal to 0. So that's going to be important. Maybe. I'll just put a maybe there. I'll make reference to it right here in just a second. It's something to keep in mind. So we can use any base of logarithm to solve the following equation. And what I will always use is the natural log, the ln. So 7 to the power of x is equal to 12. So what we're going to do is we're going to take the natural log of both sides. Now you could take log to the base b if you wanted. So you have a choice on that. It will not affect the answer. And the reason I'm putting the 12 in parentheses, normally we don't, is just to kind of emphasize that this is a function. This function, the function log to the base a of x, that is a function and x is my input. So here, the next thing I'm going to do is I'm going to use a property of our logs. So log to some base a over x raised to the r power is the same as r times log to the base a of x. So it allows me to bring the exponent on the function input out to the beginning. It removes it from the exponent. Now here, what you want to remember is that the log of 12 is a constant. I can't tell you what the value of it is. I need a calculator to approximate it. And the natural log of 7 is another constant. And we know that the natural log of 7 is not equal to 0. So the log of the only number whose log is equal to 0 is 1. So that means I can divide both sides by the log of 7, the natural log of 7. In actual math, really, the only logs that exist for us is the natural log, and we many times just refer to the natural log as log. So it's not universal, the conventions that we've used. So this is the exact answer. It cannot be further simplified. So this would be the exact answer. And don't be tempted. Don't be tempted to say this is the same as log to the natural log of 12 minus the natural log of 7, because that's wrong. What you do have is the log of a divided by b is equal to the log of a minus the log of b. But we don't have that. We have the log of 12, which is one constant, divided by the another log of 7, which is another. So let's calculate that. I've used the log of 12, so I do log of 12 divided by the log of 7. And the approximate answer there is 1.277. So I think somewhere in your exercises they asked you to approximate to the 1,000th place. So again, by reminder, here's my decimal. The first place after the decimal is a 1/10th place. The second place is a 1/100th place. And the third place is the 1/1000th place. So when they ask you to approximate to the 1,000th place, you round. If this number that follows is greater than or equal to 5, then you round up. If it's less than 5, then you leave it as it is. Okay, so this is another really nice problem. And again, with this one, you could solve it any way you want, but I'm going to go ahead and solve all of my log problems using the natural log. So this is example 3. This is problem 3. So I have 3 to the 2x minus 1. So this polynomial, 2x minus 1, is my exponent. And that's equal to 0.4 raised to the x plus 2. So what I'm going to do is I'm going to take the natural log of both sides. So these are my exponents. Recall 2x minus 1, that entire expression, it's a polynomial, is my exponent. And this is also my exponent. So by the log property I just mentioned, I can bring the exponent down in front. And then this becomes just log of 3. And this is equal to x plus 2 times log of 0.4. Now here I'm going to make a observation. This is just how I'm going to do it. I'm kind of lazy, and I can actually work with variables or constants, letters that stand for constants, easier. So I'm just going to say, let the variable be, let the constant, let B, we'll just go with that, let B stand for the constant, which is log, natural log of 3, and let C stand for the natural log of 0.4. So I'm going to rewrite this using those conventions. I have 2x minus 1 times b is equal to x plus 2 times c. Now at the end of all of this, I will go back in, and wherever I find b, I will replace it with the natural log of 3, and wherever I find c, I will replace it with the natural log of 0.4. So now I'm going to use distribution. So this is 2b x minus b is equal to c x plus 2c. So I'm solving for x. Just recall that x is our unknown. So we always have to solve for x just like normal. So I want to move all of the x terms on one side. Any term that has an x gets moved to the same side. And then what do? These two terms here have a common factor of x. So I take out that common factor. And on the assumption that 2b minus c is not equal to 0, I can divide both sides by 2b minus c. And here, I will go back up to the original now and replace b with log 3 plus 2 times the log of 0.4 over 2 times log 3 minus the log of 0.4. So I find it much easier, instead of carrying down the log of 3 and treating it as a constant, just to make this replacement right up here and just work with a much easier to write b and treat it as a constant, c as a constant. And then once I do all the algebraic manipulations, then go back through and replace them with what they are at the top. And this is the exact solution. And I'm really not interested myself in finding that out with the calculator. But if you do get your calculator and you want to experiment with it, I'm looking at my notes right here. I'm not going to waste time to do it because this is what I would want to see. It's approximately equal to minus 0.236 if you want to play around with your calculator. So here we are. We're going to have to do all of these with the calculator. So it says solve each of the following. Give your answer to the nearest thousandth. So in this one, if this were something you were to see on an exam, and I'm saying it's going to be pretty unlikely on an exam, but if you were to see it in your homework in my math lab, then it's an indication that you've got to use your calculator. So we're going to look at the first one. This is 3a. So I have e raised to the x squared is equal to 200. Now again, I'm going to solve this by taking the log of each side. But in this case, since this base here is e, since the base on the left-hand side is e, we want to use not any logarithm, but the natural log. So if it were base 10, we would use log to the base 10. If it were 3, we would use log to the base 3. So here we go. I'm going to take the natural log of both sides and remind myself that the natural log of 200 is a constant. So that's just a constant over here. Now I'm going to use the same log property that allows me to take the exponent of a value that's the input of a log and move it to the outside. Here's another important property to remember. The log to the base a of a is equal to 1. Why? Because a to the first power is equal to a, just using that little definition. So that means log to the base e of e is 1. So I get x squared is equal to log of 200. So now by using the square root property, I take the square root of both sides. So x is equal to plus or minus the square root of the log of 200. Now, if you think about it for just a second, we know since 200 is greater than 1, that the natural log of 200 is positive. Now, if this were the log of 0.12, it would be a negative number. And we would still have an answer, but it would be a complex number. But I'm pretty sure in this particular class we're dealing still with real valued functions, so you shouldn't have to worry about that. So let's calculate that, because that's what we're asked to do in the instructions. So again, bringing up the calculator. For my particular calculator here, what I do is I initiate the square root, then I'll do the natural log, 200, I hit that. So it's equal to plus or minus, and I want an answer to the nearest 1,000th. So it's 2, so I go 3 places past the decimal place. So 2.30, and since I have a 1 there, but the next digit is 8, I round up to 2. Okay. So now let's do 3b. These are actually, I always enjoyed doing logarithmic equations. When you look at them, they look just impossibly difficult to solve. But really, they're not. They're really straightforward to solve. E raised to this is a polynomial, it's raised to a polynomial power. 2x plus 1 is my exponent. Now this is multiplication here. Times e to the minus 4 power is equal to 3e. So over here, the inside is going to be that a, any number a is, I guess, let me use b, because b raised to m to the mth power times b raised to the nth power, the bases are the same. This is the very first exponent rule that we've learned, is b raised to the m plus n. So over here my bases are e. So this is e raised to the 2x plus 1 minus 4, and that's equal to 3e. So simplifying the polynomial as an exponent, that's e to the 2x plus 1 minus 4, that's to e to the, do I have an x? Oh, that's 4x. Sorry, let's get this right. So that's e to the minus 2x plus 1. And that's going to be equal to 3e. Again, our base is e, so let's take the natural log of both sides. So using the property that allows me to remove the exponent and bring it out in front as a factor times log of e. That's kind of nice because log to the base e of e is equal to 1. And over here I'm going to use the logarithmic rule that allows me to take the log of a times b is equal to the log of a plus the log of b. And I apologize because every time I see ln I just say log. And that's a long, long habit of being in math. Because really, the natural log is the only log that exists for us. So we just call it the log. So just bear with me. Old habits are hard to break, and I probably won't be able to break it. So this is going to be log 3 plus log of e. So minus 2x plus 1 times the natural log of e is 1. So that's just minus 2x plus 1. Because the natural log of e is the log to the base e of e, that's just 1. And this is log of 3. The log to the base e of e is 1. So I'm getting on down there, I'm getting closer. So now I'm just literally solving for x. So you isolate x. So that leaves me minus 2x is equal to the natural log of 3 because the 1's end up canceling. And now I'm just going to simply divide both sides by minus 2. And we want this to the nearest 1,000th. So let's do it. What I'm going to do is I'll just do the log to the base 3 divided by 2 and change the sign. And the reason I'm doing that is I don't see, I'm uncertain about that. Did that take the log of 3 divided by 2? Or did that take the log of 3 and then divide it by 2? So let's do it the way that I know will be correct. The log to the base 3 in parentheses divided by 2. And I put a negative on my answer. And what was that again? 0.549. Since the digit after 9 is 3, that's less than 5. That's the answer, 0.549. Okay. More tricks are coming. So here is another particular example. Just a lot of tricks. And to be honest with you, when we actually start examining the real world is full of exponential equations. And to solve exponential equations, we have logs. That's because they're the inverse. That's how we can get a handle of them. Here's a hint. Anything that self-replicates grows exponentially. So fire grows exponentially because it feeds on other things, which in turn feeds on other things. The reproductive rates of animals grows exponentially. Now, of course, when we model these things, rabbits can't continue to breed because if they do, eventually they'll have so many rabbits there's not enough food to eat and they'll all starve to death. So there's other natural breaking factors. The same is true with COVID-19, and it was just yesterday that AstraZeneca and the German pharmaceutical announced a vaccine that is supposed to be 90% effective if that holds. So maybe soon we can all go out and do what we want to do without worry about anything. So substitute. We're going to do a substitution. I'm going to introduce a variable u. I'm going to say u is equal to e to the x. That means u squared is equal to e to the x squared, which is equal to e to the 2x by well-known exponential laws. So that e to the 2x becomes u squared minus 4. E to the x is u plus 3 is equal to 0. So now literally I have a polynomial in the variable u. So let's factor that. So that's going to be u minus 3 times u minus 1 is equal to 0. So that means u minus 3 is equal to 0, or u minus 1 is equal to 0. That implies u is equal to 3, and that implies u is equal to 1. So let's take both of those. So that means e to the x is equal to 3. Well, that's easy to solve. We just take the natural log of each side. That means x times ln of e, which is another way of writing 1, is equal to the natural log of 3, which means since the natural log of to the base e of e is 1, that means x is equal to the natural log of 3. So that's one particular answer. And using the exact same reasoning over here, we're going to get x is equal to the natural log of 1. And what is the natural log of 1? So e so what number? Y. E raised to what value of y is equal to 1. So notice here, I rewrote, just so you're not confused, I know this is new for you, the natural log of 1 is the same thing as writing the natural log, let me do it maybe, just the log to the base e of 1. So log to the base e of 1 is equal to what number? Y. Well, that means e to the y is equal to 1, so that means y is equal to 0. So this can be further simplified to 0. And we're done. If it's a whole number, you don't have to write it out to 3 decimal places, but maybe you should. That's exact. Just leave it just like that. Don't put a decimal or anything. So now let's find out the natural. Are we still doing the decimal? Yeah, we're still doing the decimal. Let's find the natural log of 3. So it's 1.098. 8's at the thousandth place, but that's a 6, so it's 1.099. Well, I don't know that we're doing this to the nearest thousandth place or not, but if you were asked this, clearly the exact answer would be 0. I would definitely want you to realize that the natural log of 1 is equal to 0. The log to the base a of any base a of 1 is always equal to 0. And up here, natural log of 3. So those are x is in this set. So that's the solution set. And these are the exact answers. And that's what I would prefer probably. Okay. Solve each equation. So again, this is kind of weird, because now we're taking our unknown is the input of a log. So I have 7 times the natural log of some unknown number x is equal to 28. So I don't know what this is, but it's some number. And whatever that number is, I'm multiplying it by 7. So what I'm going to do is I'm going to divide both sides by 7. And that gives me that the natural log of x is equal to 4. And here, I think there's 2 ways to proceed. You just remember that the natural log of x is another way of saying log to the base e of x is equal to 4. So by definition, by the very definition of the log function, that means e raised to the 4th power is equal to x. So this implies e to the 4th power is equal to x. But we have another way of doing that as well, and this is the alternate way. And to be honest with you, it seems like this alternate way that I'm getting ready to do right now for you is the way I always did them. Probably not wisely, but I always did them that way. So let's do the natural log of x is equal to 4. So what we're going to do is we're going to raise both sides to the base of the logarithm. So if we go all the way back to the very first beginning of this lecture, e to the base log base e of x is just another way of saying x. And you get the exact same answer that way. I don't care which of the 2 methods you use, but it is an insight. There's a lot of interesting properties here. And I swear these are some of the most useful properties that we can actually deal with. So here we can we'll do it 2 ways. How's that? We'll do it by definition. So by definition, this means 2, that's my base, to the third power is equal to x cubed minus 19. But 2 to the third power is 8. So 8 is equal to x cubed minus 19. So moving that to 0, 0 is equal to x cubed minus 19 minus 8. So 0 is equal to x cubed minus 27. So that's another way of saying 27 is equal to x cubed. Now I'm going to write 27 as 3 cubed. So that tells me that x is equal to 3. The other way to do it, especially some of you will be physicists, is just immediately, let me just repeat all this over here. And after the first step, we'll pretty much get the same thing. The base is 2, so I'm going to raise this 2 to the log, to the base 2, of x cubed minus 19 is equal to 2 to the third. Since the base here and the base of the log are the same, that means this right here, the input to the function, x cubed minus 19 is equal to 8. And from here on out, it proceeds exactly to the solution the same way as we have, I guess it's this step right here. We still get the exact same answer. So those are exact values. No bother to take out this. So here we're going to have exact values. So here's the thing about this one. Here's the lesson here. The domain of the log function is all numbers greater than 0. So in our equation here, I'm taking the log, this is the base 10 log of x plus 6, and then I'm subtracting the base 10 log of x plus 2, and that's going to be equal to the log of x. So starting over here, that means x plus 6 has to be greater than 0. It means, here is the word and, x plus 2 has to be greater than 0. And here, x has to be greater than 0. Well, this implies that x has to be greater than minus 6. And it also has to be the case that x has to be greater than minus 2. And it also has to be the case that x has to be greater than 0. So what do I do? These are three constraints that have to be satisfied. So there's my 0, my minus 2, and my minus 6. So x has to be greater, so this is minus 6. Let me make that bigger so you can see it, a different color rather. Minus 6, minus 2, and 0. So x has to be bigger than all of these. So that means the first one says x is in here. The second one says x is in here. And the third says x is in here. So that means all three of these, the and means I'm taking the intersection of all these sets, so this is the one that dominates. If x is greater than 0, then x is also greater than minus 2, and x is also greater than minus 6. So whatever our answer is, if I get answers that are less than 0, they have to be, the solutions have to be excluded. And it might very well be that there is no solution to this problem. So now I'm going to use a logarithm property. So remember that the log of A minus the log of B. I'm going to do this a little bit different. I'm going to say it in the full generality. The log to the base A of x minus the log, same base, to the base A of y is equal to the log to the base A of, do you remember what it is? X divided by y. Those are our logarithm properties. So I'm going to rewrite this as log to the base 10 of x plus 6 over x plus 2 is equal to log of x. So now I'm going to use the fact that logs are one-to-one functions. So this implies x plus 6 over x plus 2 is equal to x. So what do? I multiply both sides by x plus 2 to clear the denominator. Now I'm going to get a quadratic equation. So this is going to be x plus 6 is equal to x squared plus 2x. So moving everything to the left-hand side. I get 0 is equal to x squared plus x minus 6. So does this factor? Well, let's try it out. 0 is equal to x plus 3 times x minus 2. So let's do the Tic Tac Toe Method. I know some of you can do this in your head because you've gotten really good. So this is going to be x squared. This is going to be minus 6 and x. I have no choice but to x there and x there. So I'm going to say 3 and minus 2. This gives me 3x minus 2x. It gives me 3x minus 2x is x. So that's the factorization. So that implies x plus 3 is equal to 0, which implies x is equal to minus 3. The other factor, x minus 2, is equal to 0, gives me x is equal to 2. But we have already got the constraint that x has to be greater than 0. So the only answer to my question, or to the problem, is x is equal to 2. The x is equal to minus 3 has to be rejected. So here again, I have a reminder that the domain of the log is all positive numbers. It does not include 0. The range is everything, but the domain is every real positive number. So we want to solve the following. And this is an interesting question. So this is the base 2 log in parentheses of 3x minus 7 x minus 4 is equal to 3. So the first thing we have to do is find values of x that must be excluded from any solution set. This is now, before, the only thing we had to worry about is dividing by 0. But now we have, for the first time, a function with a restricted domain. So I cannot put any function values in. This is the input of the log base 2. So I can't put any input values that are less than or equal to 0. So it's a whole new restriction that must be excluded. And ostensibly, that means values of x that make 3x minus 7 and x minus 2 x minus 4 less than or equal to 0. So what we're going to do here is we're going to take each factor, 3x minus 7, and solve the inequality. 3x minus 7 is less than or equal to 4. Here we go. Thinking about that too soon. So this is 3x less than or equal to 7. That implies that x is less than or equal to 7/3. And x minus 4 is less than or equal to 0, implies x is less than or equal to 4. And what I do is we're going to draw two number lines. And I'm going to mark out 4 and then 7/3. So 7/3 is less than 4. So it doesn't have to be to scale. 7/3 and 4. So this is going to be my 7/3 line, and this is going to be my 4 line. And what I want to do is I want to shade values of x that are less than or equal to 0. So x less than or equal to 4 makes x minus 4 less than or equal to 0. And values of x less than or equal to 7/3 make 3x minus 7 less than or equal to 0. So here is, we're going to just stipulate that this means minus. So here, from here, minus times minus gives me a plus. So that's what I'm dealing with, because minus times minus gives me a plus. So if I go all the way from minus infinity to 7/3, I'm not including 7/3 because I don't want them to be 0, then I have these two factors. I'll call that factor 1 and that factor 2. They're greater than 0. Now here I have a minus, and that's a plus. So when I multiply them together, I'm going to get a negative. So that's not going to work. But from over here, they're both going to be plus. So if I take, starting at 4, and going to infinity, the product of the two factors are also 4. So x can be either in minus infinity to 7/3, or x can be into, so acceptable answers are minus infinity to 7/3, or 4 to infinity. So now let's go about the problem of actually solving what we were given. And thankfully, solving what we were given is not as bad as you might think, although it will cause us to here it is, 3x minus 7, to pull out the quadratic equation. You won't see one like this on the test. I know I shouldn't have said that because you now just completely tuned out, right? You said, stop the video now. You might see it on your homework, you might see it on a bonus. It's equal to 3. So what I'm going to do is I'm going to raise let's just use the definition. This by definition says 2 raised to the third power is equal to the input value to my log function, 3x minus 7 times x minus 4. So 2 to the third is 8, is equal to 3x times x is 3x squared. 3x times minus 4 is minus 12x. Minus 7 times x is minus 7x. Minus 7 times minus 4 is plus 28. So I'm going to set this equal to 0. So 3x squared minus 19x plus 20 is equal to 0. So let's see if we can factor that. Purposely, a lot of these are normally in real life you would never ever expect to be so lucky as to have a polynomial you can factor. And indeed, they recently proved not more than a year ago that the set of polynomials that can be factored is almost equivalent to 0. I'll just leave it like that. It's a set of measure 0 in a very, very large, uncountably large set. So let's do 20 as well, we could do minus 4 and minus 5. So minus 3x times minus 4 is minus 12x. X times minus 5 times x is minus 5x. Okay, that's good. So 3x times x is 3x squared. Minus 4 times minus 5 is plus 20. Minus 12x minus 5x is indeed my... Nope, that's not working. Notice it's not 19x. This is equal to minus 17x. And it needs to be not minus 19x. So what if I switch? Kind of like that combination here. Then this becomes what I want it to be, right? So minus 3 times minus 5 is minus 15x. And this is minus 4x. Then I get minus 19x. So I have the factorization 0 is equal to 3x minus 4 times x minus 5. So I set each one of these values equal to 0 and solve for x. That gives me x is equal to 4/3, or x minus 5 is equal to 0 gives me x is equal to 5. So what were my constraints? So 5 is definitely over here. 5 is greater than 4. And what about 4/3? Is 4/3 less than 7/3? So let's check it out. Is 4/3? So 4/3 is less than 7/3. So why? When the numerator stays the same and I increase the denominator, then I increase the number. So 4/3 is indeed less than 7/3, and that means both of the answers are included. So my solution set is 4/3 and 5, and x is in that set. And I believe that's all we're going to do. Example 8 is another one very similar to the one I just did, and you use the exact same techniques that I did, but we're not going to do it. Just one is sufficient, in particular because I said a question like this, if it were to appear at all on an exam, it would be a bonus. So that only leaves us with example 9, and we do need to do example 9. So here we go. I think this is the last one. Yes, it is. The reason I know is because here on my paper I have at the very last box some steps for solving equations. So this is just one of these that looks much worse than it really is. So this is 9. So the natural log of e to the natural log of x minus the natural log of x minus 3 is equal to the natural log of 2. So let's do one simplification. Notice again that this is the input, e to the natural log of x. So this is just another way of saying the natural log of x, because e to the base e log of x is equal to x. So that's, as soon as you see that, it reduces really easy. So here it's easy to see that all of our values, solutions, must have x greater than 0. X has to be both greater than 0, no. X minus 3 has to be greater than 0, so x has to be greater than 3. I'm glad I did that. So the solutions have to be not greater than 0, but rather greater than 3, because we cannot have the inputs of these less than 0. So if x is greater than 3, x is also greater than 0. So by using our log problem, log properties, this is the same thing as the log of x over x minus 3 is equal to the log of 2. And now we use the fact that logs are one-to-one functions. That means x over x minus 3 is equal to 2. So we clear the denominators by multiplying both sides by x minus 3. And then we simplify. I'm going to place the minus 3 on the left and the x on the right. So 3 is equal to x. Oh, sorry. That's supposed to be 6. Because I forgot to distribute, didn't I? Here at the very end. So 6 is equal to x, and x has to be greater than 3, so my solution is just this. This is my solution. So this does have a solution, and the solution is 6. And as you'll see at the very, very bottom here, I just copied and pasted from our textbook different techniques to solve for x when you have a logarithmic equation. And that's it for 4.5.